2 kilograms, that one?
Yeah.
That's very similar to the one we did right
I
here.
was about to say, I thought that that's what he was kind of talking about.
Yeah, that actually strikes me as more of a chapter 4 problem, number 29, but.
Yeah, only because it said, when you was explaining it, you were talking about 3 squared, 4 squared, and 5 squared.
Oh.
I didn't understand that. I know it's Pythagorean Theorem, but.
All right, so. So this was 3 newtons, 4 newtons, and 2 kilograms.
Did you say it was something?
Pardon?
I don't have the question written down, but I
Oh.
didn't think it was talking about like that. And that's chapter 5?
Yes, chapter 5. Is that what you're talking about?
See, and I'm making careless mistakes, it says blah, blah, blah. Oh, yeah, that's what I'm talking about, sir.
Okay. You just need to go over it.
Yeah.
All right, so. Yeah, he put it under chapter 5, so it officially counts as a chapter 5 question, but the nature of the question, I guess it's the addition of vectors. That's what makes it a chapter 5 from Hewitt's point of view. If I have vectors of the same type, if I'm adding vectors that are perpendicular to each other, so at right angle, then you're gonna, well, whenever you add vectors, you add head to tail. So you take one of the vectors, you draw it out. That's supposed to be straight, so we can pretend. Or one more try. Okay. All right, so that's 3 newtons this way. So now I'm here. So I draw the next vector that's going up. Now he doesn't specify to the right and up. All he says is that they're a right angle to each other. My resultant is from where I begin to where I end. And since I have a right triangle here, I find the hypotenuse or the magnitude of this using Pythagorean theorem. So we label that C as A and B. The A squared plus B squared equals C squared. Or C is going to be the square root of A squared plus B squared. And that's the equation that he has right above it, the resultant of 2 vectors at right angles to each other. And then he's got this R equals square root of x squared plus y squared.
When you were explaining this isn't how you was going, it wasn't explaining it like that.
The beautiful thing about it is there's multiple ways of looking at it.
Thank you. Okay,
Or some people find it a real nuisance that there's multiple ways of looking at it. But
me, probably, sorry.
so that's what's going on here. So basically, the formula that he gives in the book is Pythagorean theorem. And also, therefore, in this particular case, this becomes the square root of 3 squared plus 4 squared, which is 5. 3, 4, 5 triangle, Pythagorean triplet. And so the magnitude of the net force is 5 newtons. And that's going to be equal to the mass times the magnitude of the acceleration. And so that's where we get. The math problem is 5 divided by 2, or 2.5. Or 5 halves for the fraction fans. And since I started with standard units of newtons and kilograms, this will be standard in the end of liters per second squared.
Okay, so we got 5 and then we had to divide it by the kilograms because of what?
The relationship between force and acceleration, the fact that force is equal to mass times acceleration. Or some texts will write it in a slightly different form. This is the form that that I prefer because Jonathan scars are fractions. Acceleration is force divided by mass.
Okay,
And so to define the acceleration, you take the force and divide by whatever mass is being forced.
okay, okay.
Oh, okay. And I think that's, yeah.
Okay, thank you.
Simple. Other questions from 4 or 5?
31.
The cart and trailer.
Yeah.
Van exerts force on trailers of different masses M. Compared with the force exerted on each trailer, rate the magnitude of the forces each trailer exerts on the van. Yeah, that is a really awkward wording if the answer weren't what it is. I would look at that and go, there's no way of knowing exactly what he means. But because of Newton's third law, his wording can be as awkward as he wants it to be. I have the trailer being pulled by a vehicle. Beautiful. If I treat the trailer and the van as separate objects and think about the forces involved, I've got a weight of the truck, what do we call it? Van. I have weight of van. Let's put the ground into it. I have weight of van. I have weight of trailer. Weight of trailer. I have a normal force acting up. We'll call it y sub v. Y sub v. Trailer's also touching the ground. Y sub t. Y sub t. I'm going down the checklist here. Weight's done, normal force is done. There's no other, really. Friction, there's friction acting this way on the wheel. Friction acting back of F sub V. Friction acting back. Because it's the vehicle that's pulling it, its tires are moving around, from our point of view, clockwise. So at the bottom, the wheel wants to go that way, and friction opposes it by pushing in the other direction. Whereas over here, if it were frictionless, this wheel wouldn't turn at all. So the friction on this wheel, because there's no engine driving the wheels, friction is going this way. So this is friction on the trailer, friction on trailer. And we're left with tension. We got this pulling thing. The van is pulling the trailer, so the trailer is being pulled this way with some sort of tension, and the trailer is pulling back on it. If you've ever pulled a trailer, you know you're pulling something because you're feeling the drag on the vehicle. Unless you have, a vehicle designed for pulling, in which case you might not feel it. The question is comparing these two. But by Newton's third law, they are equal in magnitude, opposite in direction. It does not matter what the mass is of either object, doesn't matter how fast they're going, those forces are going to be the same magnitude. So the wording compared with the force exerted on each trailer, rank the magnitudes of the forces each trailer exerted on the van. If they were not the same, I have no idea what he's actually asking. Questions on this one? All right. Other questions on 4 and 5?